Assalamu alaikum, my dear students. How are you? Hope fine and okay. We last time we have finished chapter number 5, that was gravitation, and I hope you have learned a lot from the previous chapter. Now we are starting our new chapter, which is about work and energy. I hope you all have your book open at the right page 119. In this chapter, I will explain you about work, energy, and power. Although in the title of the chapter, power is not mentioned, but in the chapter it is indeed. Work, energy, and power are very much essential to physics. And you know that when I was explaining to you the importance of physics at one point, then I told you that physics is a gateway to energy. From my this statement, you will truly understand the importance of work, energy, and power. Work, energy, and power are frequently used in everyday language, and they are very closely linked together, and most often we do not differentiate between them, although there is a chalk and cheese difference between these three, and we need to define and explain them very precisely and clearly. Uh, if you uh, if you see, look, work is in fact the kind of or the method of transfer of energy in one way I would like, and later on I'll be explaining my this statement, right? That work help us in transferring energy, while energy is the ability or the capacity of the body to do work, or it is the, you may say that the quantitative property that must be transferred to an object to perform certain tasks. For example, you see that we need energy for our everyday task. For example, for cooking, for running, even we cannot sleep if we do not have energy. In order to sleep comfortably, we need energy. We need energy to write on the board. Right at this time, when you may be noting my points, you were in your notebook, you will need energy to write on your notebook. If you ask a sick or a ill person to write something, he wouldn't be able to write it comfortably. Why? Because he or she lacks energy. So if we lack energy, then we will not be able to perform any job. Then there is power also, and I would like to write the power or to include power to my this chapter also, because power is also very important. We need to explain the power also. Power in different from work and energy, because power is a kind, you cannot say that it is a speed or like a kind of speed, you may say. The power tells us how fast work is done, how fast energy is converted from one form to another. For example, if you are moving upstairs, so if you move through the left or if you move through the stair, in both the cases work done is the same, but in case of the left, the work done is very fast, and in case of the stair, it is slow. So that is the difference between these three. Now, let us start from our first topic, work. a kind of physical quantity in the physics. Now, the term work was first introduced in 1826 by the French mathematician Gaisberg. He introduced the idea of the work. The idea, the concept of the work is different than from the ordinary concept of the then from the day-to-day life concept of the work. For example, if I tell you that, oh, I have done a lot of work while preparing this slide or this lecture, then okay, you might be thinking that, oh, sir is tired and he has done a lot of work. But in physics, this is not a work done. And you'll be very much surprised that despite my so much effort, right, and this long stay on my chair, I'm not doing any work done. But what we can say, the physics is not accepting it, and we have a reason why the physics is not accepting it. The reason is very interesting, and inshallah, I will be explaining to you all these things. First of all, I just want to introduce the work to you generally. I just want to differentiate the work from the ordinary meaning of the work, right? Like for example, from the mental work, right? From that kind of work, I just want to differentiate the concept of the work in physics. So in physics, work is done when a force causing the movement or the displacement of an object. For example, a man pushing the box along a horizontal on the ground. You see, look at this uh, animation. You see, the man is pushing the cart in the direction of what? In the along the horizontal direction. So you see, as he apply a force, look, he is applying a force. As you see, look, he is applying a force, and the force is in this direction. The arrow indicate force, and this is displacement, and that was the force, you see. So look, that is what? That is the we say that work is done, the man is doing work. So when a man pushes the box along the horizontal on the ground, then we say that the man is doing work done. Why? Because the force causes a displacement. The force causes the object to displace. So we say that work is done. When you are lifting a bag full of the book upon your shoulder, so we say that you are doing a work done at the pick up time when you pick your bag up to your shoulder. So we say that work is done. A book falling off a table and hitting the ground would be also considered as a work done. You see, look, the book fall, the diary fall, and we say that work is done, right? Because the gravity, you see, look, when the book falls, so you know there is a force which we call weight that acts in the downward direction, and you see the book start from here, and when it arrive on the ground to that depth, you see that the book covers some distance also in the downward direction. So we say that work is done. Weight lifter lifting a barbell. In this case, you see, look at this thing. In this case, the man is doing work done. You see, look, he is doing a work done as he lifts the bar. The weightlifter lifts the barbell, so he is doing work done, right? Now, these are the example where you have seen that a force causes the object to move or to displace. And in physics, this phenomena is known as a work done. Now, when there will be no work done, right? When we say that no work is no work will be done. So when a force, despite acting on an object, does not cause it to displace, or when a force and displacement are not in the parallel direction, or when they are at right angle to each other. So let us give you some example here also. For example, it is a frustrated person pushing against a wall only to exhaust himself, is not doing any work because the wall does not move. Let us see here. He is just pushing on the wall. Is let me do this, explain to you. Let me make the wall a bit visible to you. So you see, the man is just pushing on the wall, as you see. Look, he is pushing on the wall, but he is not doing any work done. Why? Because there is a force, but there is no displacement. And work, which we have defined, that work is only done when the force causes the object to displace. So here in this case, you do not see the wall to move. The wall displacement is what? The wall displacement is zero. The wall does not move, and the man constantly apply what a force on the wall. Let us see. Look, he is pushing the wall, but the wall does not move. There is no motion in the wall. So we cannot say that the man is doing work done. This is one example. Another example, a car with its engine switched on. You might have seen in a car parking sometime when your papa he switched on your car engine. The car engine is running, but the car is not traveling any distance, right? So we say that the car is not doing any work done. Similarly, just they take the example of the aeroplane, that the aeroplane at the airport, you see that the aeroplane engine is switched on, and even you are instructed not to go near to it, and you see that still the aeroplane does not do any work done. Why? Because there is a force acting, but that force does not cause the aeroplane to move. So therefore, no work is done. The next, a very interesting example is that you see a waiter, that is here. You just look here. You see, look at this example. This is very interesting example, and later on I'll be showing you this thing, inshallah, mathematically also. You see a car. You see, look, you see a car with its engine. Okay, it is not. It won't be visible to you. One highlight is in. You see, a waiter carrying a tray above his head, supported by one arm, as she walk at a steady pace across a room. Might think she is working hard, but in fact, but in fact, she is not doing any work done. Look how. See why? Because no work is done on this. It is one of the reason that, look, as she is moving in this direction, right? She is moving this. In fact, that is there is no work done by the gravity. This force, the gravitational force, does not do any work done, right? You see, look at this thing here, because this is the gravity does not cause it to displace in the direction of the force. If it is to be falling, then work will be done by the gravity, but in this case no work is done, although she might be even spying, but she is not doing any work done. Why? Later on I'll be telling to you, her muscle does work, right? Why? Because it is constantly contracting and expanding, so the muscle exert a force and the muscle displaces, so her muscle does work, but the the work done on this tray is zero. By the work done by the gravitational force, the gravitational force does not do work done on it. Why? Because the displacement is in this direction and the force is in this direction, and for the work they must be in the same direction, right? And later on I'll be telling to you one important concept of the work done, that why this thing is going to happen. The reason is very simple. There is no work done in that case. I just want to refer to this case. That is, in this case, there is in this case there is no work done. There is no work done because because the no work done by gravity, because the energy is not converted from from potential to kinetic. The energy of this tray, it is constant, right, as she move. So the energy, there is no change in the energy of the tray, therefore there is no work done. So what does this mean? That the work done is in fact, it is related to what? The concept of the work. Yeah, the work done in physics is related that work is done only when energy is converted from one form from one form from one form to another another form. Then we say that work is done. Right, in this case you just see, look what is going to happen in this case. Look at this case. You see, yes. You see, in this case the man has potential energy stored in his body. He has a potential energy in his muscle. As he pushed the cart, the potential energy stored in his muscle changes into the kinetic energy of the cart, and the cart displaces. And we say work is done. So the work done involves energy changes. Look in this animation here. The book has a potential energy, and you know when the book fall, the potential energy of the book changes into a kinetic energy. So energy changes is involved, energy changes are involved, and therefore work is done. And look at this case here. What is going to happen? When the weightlifter lifts the barbell, then at this point, look, he has a kinetic energy because he is moving the barbell. And at that height, when the barbell reach this height, the barbell has potential energy. Later on, I will be explaining this thing. So work, in fact, involve energy changes. It involves what? It involves energy changes. Another concept for the work done, I would like to tell you that work done, in fact, that is the work done, in fact, is what? Nothing, but it is the transfer of, that is the work done is the method of transfer of energy. By the help of work, we transfer energy from one system to another. For example, look, when you switch on the light, the electron moves in a wire. So when the electron moves, there is electrical force acting on the electron that causes the electron to displace in the wire. And when the electron displaces in a wire, it says a kinetic energy. And that kinetic energy changes into light energy when the electron pass through the filament of the bulb, and we say that work is done. So work done is always involved in energy changes. That is the real concept behind the work. That work is in fact the method of transfer of energy. It helps transfer energy from one form into another due to the actual displacement of the object. So it is the transfer of energy when there is displacement, right? So that is the concept of the word. And so what is our conclusion? Our conclusion is that for the work to occur, a force has to be exerted on an object, causing it to move in the direction of the force. Now the physics of the work done. The physics of the work done is in fact, let us see that in how we can define the work done. Work is said to be done when when work is said to be done when a force acts on the body, when a force acts on the body and displaces it in the direction and displaces it in the direction of the force applied. That is work done physically. So work is said to be done when a force acts on the body and displaces it in the direction of the force. It is the more precisely we can say, or mathematically we can say, that work is of the product of force and displacement. Mathematically, we can write that that work equals force times displacement. Force times displacement. Or we can write that work equals F into S, where F is the force applied and S is the distance moved by the object. Like, I just want to do it like this. The work done, the work done equals F into thumb rule, F into S. If you place your thumb here, so work done will be equal to what? If you place, like, just consider this your thumb, then work done will be equal to F into S. F, so this is the work done, W. F, you just place your thumb here, so work done will be equal to force will be equal to work done by the distance. So this is a memorization rule rather. The next important point here is that work done, the SI unit, this is too big. The SI unit of work done, SI unit of work done is joule, written as joule, and this such that 1 joule equals Newton meter, right? So that is equal to what? That is equal to joule. Now how we can define 1 joule? We can define 1 joule. A work is said to be 1 joule if 1 Newton force acts on a body and displaces it through 1 meter in the direction of the applied force. Work in work is a scalar quantity. It is what? It is a scalar quantity. What does this means? That it does not need any direction, right? Work, although if you just see, it involves what? The work done involves, it involves force, which is a vector quantity. It involves displacement, which is a vector quantity. But the work done by itself is what? It is a scalar one. Now you see, look, there is a clear distinction between this big W and this small w. You see this small w bold like this. This is for weight. Okay, you should not confuse this thing. While this capital W Small w is for weight and the capital W is for work done. So you must know this thing. So that is what that is all about the work done. That work done is the work is said to be done when a force is on a body and causes it to displace in the direction of the force. That will be a work done. Now let us do some mathematics. You see, in this case, we wish to calculate, we want to calculate the work done. Now let us see that, okay, in this diagram, the main pushes the card or displaces the card from what? From, he is displacing it from the point A to the point B. During this displacement, during this displacement, you see how much force is needed for this displacement. The force applied by the man is 12 Newton, right? And how much distance he covers? The distance he covers is, that is 5 meter. So what is the total work done in this case? It will be Fs, and that will be 12 Newton into 5 meter, like that, and it will be 60 Newton meter, or it will be equal 60 joule. Later on I will be using my this one uh, animation to calculate the energy. I will be using this to calculate the power also. That what is the power also in this case. So this is how we can calculate the work done during this. So a man need what, 60 joule of energy to push a cart from the point A to the point B through 5 meter when he applies a 12 Newton force. So this is how you can apply the concept of the force to calculate the work done. So I hope you have got the idea of the concept of the work done. Now, in the next lecture, inshallah, I will be explaining to you that how we can calculate the work done when the force is not in the direction of displacement. So that will be our next. That will be our next topic. That what will happen. That is when force is not in the direction of displacement, is not in the direction of displacement, direction of displacement, then how we will find the work done. The very similar situation, for example, look, if I just give you the a kind of situation where, for example, there is a man, the man is pushing the cart like this one. You just see there is a man, and the man is pushing the cart in this way. Let me make a box for you. Look at this box, you see, and look, the box is being pulled in this direction. You see, look, there is a force acting on the box, right? From the box has to be displaced from the point A to the point B. After some time, the box new position will be this one. Okay, you see, with the force acting on it in this direction, and you have seen that the net displacement here, that the box cos S, it is this one. Now you see, look, you are applying the force in this direction. As you see, the force is purely neither in the horizontal direction nor completely in the vertical direction. and the displacement is completely horizontal, right? Then what will be the work done in this case? A bit complicated, but not that much, inshallah. So how we will calculate the work done? Because you see the force is now not in the direction of displacement. Then what we will do to calculate the work done? Inshallah, we will do this in our next lecture.